In this video, I'm going to talk about a solution to the linear time variance system called LTV. In the previous video, I talked about how to compute a solution to the linear time invariance system given by the standard ABCD form, which is x dot t is 8, xt plus but, yt is cxt plus dut. So that's for linear time invariance system. For linear time invariance system, those A, and B, and C, and D can be time variant as shown in the beginning of this slide. So this is the general form of the linear time variance system, and given this form, we couldn't use the Laplace transform approach that I mentioned in the previous in the solution for the linear time invariance system. So we have to come up with another approach to find a solution to a linear time variance system. Okay, so the general approach to find a solution to a linear time variance system is to first look at a simple one, which is just be given by x dot t is at times xt. So without talking about a solution to this general form, let's take a look at this special form. So which means I don't look at the y sub t. Also, I don't have the input u sub t. I just have x dot t is at times xt, which is just the one component of my of the first equation in my linear time variance system. Okay, so for this one, if I give an initial condition which is xt0 is the initial condition for this differential equation, the solution of xt over here to this equation is given by xt is phi t t0 xt0. So this is my initial condition. This is my another one. Okay, we call this one a transition matrix, which means my solution is xt is given by the product of two phi is basically a matrix. So this is a vector, so it's a matrix times a vector, and this phi t and t0 is called transition matrix. In particular, this transition matrix is given by this form, okay, which is phi t and t0 is equal to this one is identity matrix, which is the same size of my matrix A, and then the second one is integration from t0 to t of a sigma 1 d sigma 1. Okay, well, this happens. I'll give more example later on how to compute this one individually. Okay, so generally speaking, you give this is linear time variance system. This is a sub t, right? You replace this t variable by a sigma 1 and you integrate that over sigma 1. Okay, this is the first component in my transition matrix. The second component is integration from t0 to t. Okay, so remember here the integration from always from t0 to t for the very last one. Okay, very left one. You do a sigma 1. Okay, then this here is integrate from t0 to sigma 1. This is not integrate from t0 to sigma to t, but to sigma 1, and then integrate a sigma 2 and d sigma 2 and d sigma 1. You basically have double integration, integrate over sigma 2 and sigma 1. Of course, one thing you want to pay attention to is you almost integration of a sigma 2 over sigma 2 from t0 to sigma 1, which means this one, this portion will give me this is a function, some function, let's say a tilde function of sigma 1. You time a sigma 1 and then integrate over sigma 1 again. So you have to integration twice, okay? Over sigma 2 first, then over sigma 1, okay? So this is the second term. The third term will be you do almost follow the same principle. You stick integration from t0 to t a sigma 1 and times integration t0 to t0 to t, sorry, here. This is the integration from t0 to sigma 1, a sigma 2, and then you have integration from t0 sigma 2 and a sigma 3, d sigma 3. So when this happens, you almost first integration this, I'm going a sequence, you first integration this guy. Okay, this is basically a function of sigma 2, and then integration of this term. This gives us a function of sigma 1, and then integration last one, you integration over sigma 1 over t0 to t. So this will give you a function of t0 and t basically, and t0 initial time, and t is the current time t. Okay. Okay, so you can there will be many more terms. You should have many more terms until infinite number of terms. Okay, they follow the same pattern basically. So if I write over here, the fourth term would be something like this: T0 to Ta sigma 1, and T0 to sigma 1 A sigma 2, integration T0 to sigma 2 A sigma 3, integration from T0 to sigma 4, yes, A sigma 4, you have D sigma 4, D sigma 3, D sigma 2, D sigma 1. Okay, so that's what you have in for the fourth term. You can follow the same pattern to find all other terms. Okay, so basically you can see this is a very complicated process because you involve many terms. Okay, the whole idea is this will give our analytical solutions. I'll talk about some of the practical methods we compute the solution later on. So this transition matrix, all this one, the transition matrix is also called, all these terms, all the infinite number of terms is also called Pinot-Baker series. So it's a series of terms whose sum will form this transition matrix. Okay. Alright, at least we know the solution to it. So it may be a little bit complex to compute it. So now I'll give you two examples how we actually compute the integrations. I'll give you two examples. One is this term, the second term is third term. Okay, the first term is identity is pretty easy to know. It's just the same size of my A matrix and its identity matrix, which means I have something like this: 1 0 0 1. If A is 2 by 2, okay. Alright, so give you an example. Let's say, what if I have A sub t, which is given t 1 0 t. So this is my matrix 2 by 2. Okay, so for this case, I know the identity for this guy will be just equal to 1 0 0 1. So it's 2 by 2. So, okay, matrix. Assume here t0 is 0. Okay, make it a little bit simple. T0 just 0. Okay, so I want to compute this second term and the third term to see how complex that would be. Okay. Alright, so the first one is to integration for A sigma 1 and D sigma 1, integration from T0 to T. T0 is 0, so it's integration from 0 to T. Okay, and A sigma and D sigma, what you do is just replace every T here by sigma 1. So I have here is integration from 0 to T, sigma 1, 1, 0, sigma 1, D sigma. Okay, so integration of a matrix is just integration of each component. Okay, you do integration of each component of your matrix, and that's quite straightforward. So after you do that, you just do integration, very standard, and then you find a solution. Okay, that's my final integration. Okay, pretty straightforward for second term. So third term can be a little bit complex. The whole principle is the same as this one. The only difference is you have two integrations. So integration from 0 to t and sigma 1 0 0 sigma 1. Here again you have to replace this by sigma 1. Okay, a all t by sigma 1. Then integration from 0 to sigma 1. So pay attention to the upper limit. This is not t. This is not a t. This is sigma 1. And here is a sigma 2, which means replace every t by sigma 2. So you have sigma 2, 1, 0, sigma 2, d sigma 2 is d sigma 1. So as mentioned over here, so you first do integration of the internal one, integration, you sort of get a function of a sigma 1, okay? So here, I first keep the first component part be the same. I just do integration of this whole piece, okay, which is given by this. What I do over here, I just copy the idea over here. The only difference I replace t by sigma 1, okay? So just copy over here to here and replace t by sigma 1, okay? Then do the multiplications of the two matrices, okay? So this is the product of these two, okay? Then you do integration of this component, as I mentioned over here. Again, the integration will be the integration of each component, okay? So I won't talk about the detailed computation, it's pretty straightforward. After you do that, you get the final result is 1/8 t4 to the fourth, 1/2 t to the cube, and 0, and 1/8 to t to the fourth. Okay, so that's my computation for the two terms. You can imagine as this integration goes more and more complex, integration can be more challenging. So the Pinot-Baker series typically give you an analytical solution, but actually give you a systematic solution. But it's not a. It's very hard to use it to compute the general solution for any matrix A. Okay, for any A sub t. Okay. All right. So in the next few minutes, I'll talk a little bit about how use a what a product transition matrix and how we actually figure out a solution of a solution of linear time invariant system. Okay. So some are nice property for the transit matrix. The first property transit matrix is phi of t to t is identity. You basically transition from yourself to yourself. You sort of can see if I do the integration from t to t, right? This is t to t to t, because the integration all zero. For all the terms that zero. You only have is that identity. Yeah, that's pretty straightforward, you can tell. Okay? The other one is the phi of t dot t0 is the inverse of phi from t0 t. So which means you transition from, you can also imagine this is your transition from t0 to t, okay? This is your t from t to t0. Yeah, you can sort of see from they are kind of opposite, okay? Yeah, they are, one is transition from t0 to t, one is from t to t0, okay? The third part of a transition matrix, the transition from t0 to t is the same as you first transition from t0 to t1, and then you transition from t1 to t. If I draw a time like this, okay, this is my t, okay. So at this point, this is, let's say this is t0, okay, this is t1, this is t, okay. For example, you find sort of solution like this, okay. So the transition from t naught, this is my y sub t, let's do it over here. So this is my x of t, sorry, x of t, okay. So you transition from xt to xt0 to xt1, okay, is so your transition from this state to this state, okay, the same as the transition from this state to first this state, and then this state to this state. You do the multiplication. That's what it means in terms of the last property. Of course, you can add more. You can say I first transition from this guy, then transition to t sub 2, for example, this is t2. Okay, then transition to t3. So basically, you have phi t naught is phi t2 phi t2 t1 phi t1 t0. That's also okay. You can add as many as you want. Okay, but pay attention to the order. You basically left multiply. Okay, don't do the right arm. It's different, so it's not phi t1 t0. You cannot switch the order. T1 and T2 and T1 and phi T and T2. This is not true. Okay, the order has to be correct. Okay. So now let's talk a little bit about the solution to the general linear time invariant system. So in the previous part, I just talked about what's the solution to this system. Okay, this is different from the original the linear time invariant system. So what is the solution to the general linear time invariant system? Okay, so if I give you this general linear time invariant system, assuming here this phi t and t0, so this is transition. This is a transition matrix for x dot t, which is at xt. So this is my transition matrix for this x dot t is at xt. Okay. Now my solution for the general this term, so this the general linear time invariant system. So this is my solution. Xt is given by phi t0 of x0, assuming here I have given initial condition of x0, okay. So at phi t0 x0 plus integration from 0 to t phi t sigma b sigma u sigma a d sigma, and yt is ct phi t0, this is transition matrix x0 plus ct integration 0 to t phi t sigma b sigma u sigma d sigma plus dt and ut. So this is the solution to general linear time invariant system. You can also replace every zero, okay, by t0. Okay, I emphasize over here. You can replace t0 by t0, assuming you have another initial condition, okay, which is x t0 instead of the standard linear, instead of the initial condition, which is x0. So the black one represents when you have initial condition given by x0, initial time is 0. When initial time is not 0, replace every 0 over here that I highlight over here by t0. That's the solution of the general linear time invariant system given initial condition at non-zero initial time. Okay. All right. So now let's give a figure example talking about how we really compute that. So in general, for a given general A sub t, it's very difficult to compute the transition matrix. Okay, otherwise it would be the same as linear time invariant system. It's not very challenging. Typically, if the computation of the solution for the linear time invariant system can be really complex. So talk about some cases that it's easy to compute the solution for the linear time variant system. Okay. So the first example shows x top t is atxt, which is at when at is 000t. Okay, so the main part I want to emphasize here is the compute the transition matrix. If we know the structure of the solution of the transition matrix, then we can do the computation according to this. So once we know the transition matrix, okay, we can use this one to compute the solution. It wouldn't be very challenging. Okay, just could be very complex. There won't be issue with computing the final solution to the linear time invariant system. Okay, so for this one, let's compute what is transition matrix. Okay, the transition matrix, this is 000t. Okay, so we can use the definition. Okay, the definition is, well, I have to compute this is using Pinot-Bakes series. So the phi t0 is identity plus integration from t0 to t a sigma 1 d sigma 1 plus integration from 0 to t a sigma 1 integration 0 sigma 1 a sigma 2 d sigma 2 d sigma, so on and so forth. That's a Pinot-Bakes series. Okay, here the initial condition is 0. Okay, if you can see over here, from here I have a general initial condition. Now for this case I have 0 initial condition, so a zero initial time, so it's a little bit easier to do. Alright, so because A is 2 by 2 matrix, so identity is just 2 by 2 matrix, the same as size of the matrix of A. So it's 0, 1, 1, 0. So the second one is, as I mentioned in the example, in the pre-example, is integration from 0 to t, 0, 0, 0, 0, sigma 1, 0, 0. So I just have to replace this t by my sigma 1. Okay, then integration over sigma 1. The second one will be integration from 0 to t, 0, sigma 1, 0, 0. Integration from 0 to sigma 1. Okay, pay attention again, this is sigma 1. 0, sigma 2, 0, 0, d sigma 2, d sigma 1, and so on and so forth. So my hope is I don't have to compute all the high dimensional ones. I just do like maybe a couple of these, then all the high order integrations will be either 0 or I can see some patterns. Okay. So the first one, identity, I just keep it over here. The second one, integration, pretty straightforward. Okay. The third one, I just do the same thing. Okay, just do integration by do the integration of the matrix first, doing this part. Okay, so this integration, this guy is pretty straightforward. Over here, it's just given by this. Okay, now this guy, for this guy, since I already computed this one, this guy is given by this. The difference from between here and here is I replace t by sigma 1 squared. Okay, so I do this guy times this guy. Okay. Once we do the multiplication of the two matrices, I can find out the product is just 0, 0, 0, 0. Okay. Now this 0 make it simple. Integration of 0, 0 over any interval will still be 0, 0, 0, 0, right? So this is gone basically, right? And also for any high order integrations, they are also 0, 0, 0, 0. You can basically tell because this already you do another integration, this is still 0, right? So this is still 0. So as a matter of fact, all the high order integrations become 0. We don't have to calculate that. We only have this first two terms that are non-zero. So we put them together, you have 1, 1/2 t squared, 0, and 1. Okay? So here's a basic summary about when we use the definition to compute the transition matrix. So typical idea is to compute this transition matrix using the Pinot-Bakes series if it is easy to find patterns without needing to compute all the high dimensional integrals. If I have to compute until infinity and there's no pattern I can find out, so typically it's not easy, it's not possible you can find a solution, or at least write a solution analytically. Okay. The other special cases is when the matrix A T is a diagonal one. Okay, for example here, when A sub t is t002t and x dot t is atxt. Okay, so one find the transition matrix, okay, which is phi is given t and t naught, t and 0. Okay, the general conclusion is the transition matrix for this special case when AT is a diagonal. This is when AT, the one right here, AT is diagonal. So the transition matrix is just given by, is still a diagonal matrix. Okay, the transition matrix is still a diagonal matrix, and each diagonal entry is given by e to the integration from 0 to t tau d tau. Okay, so what I emphasize over here is you basically replace your t a function. So this is a function of t, right? You replace it by a function by tau. Let's say this is a a1 t, then you replace this by a1 tau, and you can integration of 0 to t and d tau. This is say the general is a2t. Okay, so this is you do integration of a. So basically this is the integration of a2t, a2 tau d tau. Okay, and this is you replace tau by a1 tau d tau. So this is the general the transition matrix for this form. 1a is diagonal. You can also imagine you have more terms. Okay, for this case you don't need to. You just need to change the function variables in your diagonal entries from t to tau, and then for each diagonal entry is the integration of the exponential of integration of 0 to t, and you replace the function in your diagonal entries from variable t to tau, and then you do the integration of that. So that's the transition matrix is computed. Okay, so there's no need to compute the Pinot-Bakes series. Okay, the reason why that's the case. Okay, I'm going to give you some brief explanation by why the transition matrix is given in this form. Okay, let's say right now here I want to find a solution. Okay, let's define xt to be x1t, x2t. Okay, I want to find a solution to this equation. Okay, so once I define that, I have x1 dot x2 dot t, x1 x2 dot is equal to t002t and x1t x2t. So basically, I just want to write out this form in this form. So I want to write out this form in this form. Now I want to compute the solution directly. So this one can be written into two equations. One is x1 dot t is t x1t, and x2 dot t is 2t x2t. So they are completely coupled. Okay, so we can find the solutions. Okay, so I take any one example. I don't have to compute both of them. Let's say take as the first one example. So x1 dot t is t x1t. Okay, in order to find a solution, it's pretty straightforward. I just this x1 dot t is dx1t dt and tx1t. Now I'm going to move this guy to the left, x1t to the left, and move dt to the right. Okay, so dx1t over x1t and equal to t dt. So now let's integration both sides. So let's integration of 0 to t d, because this guy is d of the natural log of x1t. Okay, the right hand side is t xt. Okay, so I do the integration of both sides, and here I do a little change of variable because this t is a little bit difficult to say. Okay, this is the same as 0 to t tau d tau. Okay, because the integration of 0 to t and is also t get a little bit confused, but I can change it to tau d tau. Okay, so the left hand side becomes natural log of x1t minus natural log x10. The right hand side is integration of 0 to t tau. Okay, d tau. Now this guy will be equal to, okay, this guy will be just do, if you do the exponential to the both side, okay, this become e to the natural log x1t minus natural log x1, I think it should be here. Natural log x1t minus natural log x1 and 0. Right hand side e to the integration 0 to t tau d tau. So this guy, integration of that, exponential that part will be x1t divided by x10 is e to the integration 0 to t tau d tau. Then we can say x1t is e to the integration 0 to t tau d tau times x10. Okay? Now, if I want to verify this, okay, since this is already said, this is my transition matrix, right? This is my transition matrix. So my solution, if I use the transition matrix, my solution will be just this is my transition matrix. My solution will be xt is x1t x2t is e to the 0 to t tau d tau 0 0 e to the integration 0 to t 2 tau d tau x10 x20. If you compute it out, you actually get the first solution, which is x1t is e to the integration of 0 to t tau d tau times x10. So which is equivalent to the result I computed here directly. Okay, so that equivalent. If you check verify, so the solution for the second guy, which is here, to this guy, is exactly this guy. So which means, yeah, that's true. My transition matrix here is correct because if I use this transition matrix, I compute the solution xt. It matched exactly what I did over here if I would compute this solution directly like this. Okay, that's why it sort of verifies that my transition matrix given here is correct. Okay. All right. So in general, if AT is diagonal, I can use this, which is phi t and t0 integration of lambda 1 tau d tau. So assume this A is diagonal. You have a lambda 1 t, lambda 2, lambda n t as my diagonal entries for my matrix A sub t. So my transition matrix phi t and t0 is integration of e to the integration of t0 to t lambda 1 tau. So this is coming from here. And d tau. What do? You change t to tau, and you do the integrations as same function over here from t0 to t. So t0 to t, that's coming from here. That's determining your lower bound and upper bound. And then you to take exponential though, or whatever you get. Similarly for the second term, so on and so forth. All diagonal entries are 0, which means it's still diagonal. Okay, so once this phi t and t0 is obtained, which is the transition matrix is obtained, and xt, yt can be computed via this following form, which is xt is phi t0 x0 plus 0 integration of 0 to t phi t sigma b sigma u sigma and d sigma. So since we already know this, yeah, we can compute this. This is given in this condition. This is b sigma u sigma given, so we can compute the product and do the integration. The y sub t, you do the same thing. Okay, the only difference is we times ct. Okay, this is already computed already. This is given, and this is already computed. We can compute this. This also can be computed, and this is given, and this is also given, and this is given. So we can compute xt and y sub t. Okay. So to summarize, generally to compute a solution to linear time variance system, we have to first compute the transition matrix. Okay. Once we compute the transition matrix, we can use this to compute the solution xt and y sub t. So for the to compute a transition matrix, typically we either use a definition using the Pinot-Baker series I mentioned over here, which will require that at a certain point we can find a pattern, like I mentioned over here. We can find some pattern one for the high dimension integral. Otherwise, we probably can say we couldn't find an analytical solution, the general solution, the solution, exact solution. Okay, or if my matrix A sub t is diagonal, so then we can find the solution, the transition matrix in this way, or in general this way. This is the transition matrix, and then we can find a solution to the linear time variance system.